Okay, so in this video we will continue working on the planetary gear assembly that we have been studying. So we have actually couple of videos that we have made on solving a particular velocity acceleration problem on a planetary gear system, and this is going to be the third video on that. And the idea basically in these videos is to solve the problem taking multiple approaches, and so in keeping with that idea, this video will also solve the acceleration problem with a slight variation, and hopefully these different approaches that we are taking to solve these problems will help you understand the techniques of solving dynamics problems. So let me just briefly explain the problem again. This is a planetary gear assembly where the outer circle represents the ring gear, the innermost gear is the sun gear, and this gear B with center B is the planetary gear. So the planetary gear is meshed with the sun gear and the ring gear, and so at the contact points of the planetary gear with the sun and the ring gear, it rolls without slipping, or basically it is meshed in the through the gear teeth. So the problem that we are working on is in regards to finding the velocity and acceleration of a point C on this planetary gear. So we note that the sun gear is turning with an angular speed of omega 1. The ring gear is turning with an angular speed of omega 2. The sun gear has a radius of r1, the ring gear has a radius of r2, the planetary gear has a radius of r3. Because it's meshed, so r3 can be calculated from r1 and r2. C is a point on the planetary gear, and at a given arbitrary instant, let C be making an angle theta with AB, where AB is the line joining the centers of the sun gear and the planetary gear. So the goal is to find the velocity and acceleration of the point C, and also we have been given this rotating triad with ER as the radial direction, E phi kind of in the direction of the angle that is being made by AB, and EZ is mutually perpendicular. So we have solved the problem of finding the velocity and acceleration using two different rotating frames. So in the first attempt that we did, our rotating frame was fixed to this planetary gear. In the second attempt that we made, our rotating frame was essentially rotating with AB. So it was essentially rotating with this triad ER, E phi, EZ. In this particular video, what we'll do is we will show how we can just take the velocity and do a direct differentiation to get the acceleration. So instead of using the relative velocity and relative acceleration equations that we have for rotating frames, here we are just going to do direct differentiations. And this is to highlight that indeed direct differentiation is a viable approach for solving many problems in kinematics when it comes to rigid bodies or particles. It is just that in certain cases the direct differentiation approach can become more cumbersome, and you may need to define some extra variables in order to do the direct differentiation. Another thing to keep in mind when you use the direct differentiation is to avoid using any special configurations. So if you avoid using, if you use any special configuration, then what happens is that there is a tendency that you will forget to do all the differentiations and hence the velocity or acceleration expressions that you get would be incorrect. So for instance, if a disk is rolling on a horizontal surface and you want to find the velocity on the top of the disk, if you right away assume the angle theta to be equal to 0 or 180 depending on how you define the angle theta. So if you input that angle in your position variable or your position expression, then your velocity is not going to be correct, your acceleration is not going to be correct. So the main idea when you do direct differentiation is to consider the most general configuration, where you express the configuration in terms of all variables that are needed to define the configuration, and then take the derivative. And that way you get the right velocity and accelerations. But in the process, as I mentioned, it can get a little bit cumbersome. But here we'll not start with position, although you can do that here. You can say that, well, I'm going to first write the position of the point C, and A is a fixed point, so C with respect to A, and then I'm going to differentiate to get the velocity, and then once I have the velocity, I'm going to differentiate to get the acceleration. All that can be done, but in the interest of time, what we'll do is we will show you the derivation of the acceleration, and in particular this derivation will be interesting because the unit vectors that we have considered, ER and Eφ, are not fixed unit vectors. They are not inertial, they are non-inertial, they are rotating unit vectors. So let us do the direct differentiation. So I have written the velocity expression in the interest of time. This is something we had derived, and I have also written a an angular velocity expression, which we will get to shortly as we take the direct derivative. In addition, I have also shown how the triad is defined. Basically, the triad is defined, it's a right-handed triad system, and it is such that ER cross Eφ points us to the direction of EZ, and so on. Okay, so this also defines how the cross products between the different unit vectors will take place. Right? So now let's go about the acceleration. So acceleration of C is going to be Vc dot. Okay, and so Vc dot is going to be basically just the derivative of the velocity here because of the approach that we are taking of direct differentiation. So if I differentiate this expression, so first let us take this square bracket. If I differentiate it with respect to time, what I have is minus theta dot sine theta times omega 2 r2 minus omega 1 r1 divided by 2 Eφ. Now keep in mind that omega 1 omega 2, so this is omega 1 omega 2, r1 r2 are constants. R1 r2 are of course geometric constants. Omega 1 omega 2 are given to be constant angular velocities, so we don't need to differentiate any of these terms over here. Now that's the differentiation of the term within the square brackets, and keep in mind that Eφ now, and this is where we need to pay attention, because when we do the direct differentiation approach, if you are expressing the vector in terms of a rotating frame or a rotating triad, then you cannot just leave that unit vector like that. You have to take the derivative of that. With that you will get the total derivative. So what we need to do is we need to take this whole term within the square brackets, which I'm going to represent as square brackets with a dot, and then I need to do Eφ dot, because clearly as AB turns and ER is in the direction of AB, then ER is changing direction, Eφ is also changing direction, and if a unit vector changes direction, it has a derivative. Okay, so now let's go to the next term, and we will calculate this derivative, but let's go to the next one. So next one is this, so we will have negative theta dot cosine theta omega 2 r2 minus omega 1 r1 over 2 ER plus, and let me just indicate this actually I'll put a minus because there is a minus sign here. This term within square brackets with two dots times sine theta times ER dot. Okay, so now E phi dot is going to be, so E phi dot is going to be the angular velocity of E phi cross E phi. Okay, so E phi dot is going to be the angular velocity of that unit vector cross that unit vector. Now, what is the angular velocity of the unit vector? Well, by virtue of the fact that ER is always in the direction of AB, then the angular velocity of this triad is the angular velocity of AB. So it is essentially omega AB cross E phi. So rate of change of an unit vector is given by the angular velocity, the absolute total angular velocity of that unit vector cross the unit vector itself. So we have the expression of that, and so if you take this cross product, you will have EZ cross E phi. So if you do EZ cross E phi, you will be negative ER. So basically this will end up with negative omega 2 R2 plus omega 1 R1 divided by R1 plus R2 ER. Yes, check. Yes. And similarly, if I do ER dot, it is going to be omega AB cross ER, which is going to be, so omega AB cross ER is going to do EZ cross ER, and EZ cross ER gives us E phi. So you are going to have omega 2 R2 plus omega 1 R1 divided by R1 plus R2 E phi. Okay, so that's the so this is omega 2 R2 plus omega 1 R1 divided by R1 plus R2 multiplied by E phi. Okay, so we have the unit vectors. So now one thing that we need to resolve still is this theta dot. So we need to find theta dot, and I'm just going to, I'll not do the derivation. The derivation of theta dot was already there in our previous video. So what I'm going to do is I'm going to just take the expression from there. Okay, so the expression for theta dot that we have found is, and assume that this has been calculated before, just in the interest of time we are not doing that derivation here. So it is omega 2 R2 minus omega 1 R1 divided by R2 minus R1 minus omega 2 R2 plus omega 1 R1 divided by R1 plus R2 in the EZ direction. Okay, so that's the expression for theta dot. So imagine that if you were doing this direct differentiation based approach to find out the velocity and acceleration, these angular velocities like omega AB and theta dot would have to be determined by you. Okay, so here we are just saving some time by taking these values or these expressions from the previous methods that we have used to solve this problem. Okay, so let us go ahead with the expansion of this acceleration expression. So AC is then going to be equal to negative omega 2 R2 minus omega 1 R1 divided by 2 sine theta times theta dot. Theta dot is let me do the following. Let me just Well, let me just write the expression first. Omega 2 R2 minus omega 1 R1 divided by R2 minus R1 minus omega 2 R2 plus omega 1 R1 divided by R1 plus R2 this is in the direction of E phi, right? Then we are going to have this rather large expression, which is half of omega 1 R1 plus omega 2 R2 plus cosine theta times omega 2 R2 minus omega 1 R1 divided by 2 times E phi dot. So E phi dot is going to be negative omega 2 R2 plus omega 1 R1 divided by R1 plus R2 times ER. Okay. And let me just write the expression, then I'm going to superimpose the expression on the previous page with this expression so that I can show you exactly how the expansion is being done. Minus, we will have omega 2 R2 minus omega 1 R1 divided by 2 cosine theta times theta dot, which is omega 2 R2 minus omega 1 R1 divided by R2 minus R1 minus omega 2 R2 plus omega 1 R1 divided by R1 plus R2. That's the expression of theta dot, and this whole thing is in the direction of ER. So that's that. Then we have minus, we have the term omega 2 R2 minus omega 1 R1 divided by 2 sine theta times we have ER dot, and so that is going to be omega 2 R2 plus omega 1 R1 divided by R1 plus R2 E phi. Now I must clarify that this negative is not on this term, it's on this whole term. So let me now superimpose or show both the expressions together so that you have an idea of what was done. So note here that the acceleration was written in terms of these four expressions, these four terms. The first term is in the direction E phi, okay, and it has theta dot in it, negative theta dot, sine theta, and then this term times E phi. So I have taken this term written over here with the negative sign, sine theta goes over here, and theta dot has been replaced by its expression, and you have E phi multiplying with it. Now this second term is basically this guy. So what I have done is I have taken this term in square brackets, written it over here, and I have taken the expression of E phi dot, which is in the direction of ER, and I have written the expression here. Then we go to this third term. This third term has this negative sign. It has the omega 2 R2 minus omega 1 R1 divided by 2 times the cosine theta times theta dot. So I have written the expression for theta dot, and it's in the direction of ER, okay, because here is the unit vector. The last term has a negative sign associated with it, so I have taken that negative sign. The square bracket term is basically this guy, which I have just replicated here, copied here, sine theta here, being taken from this this expression, and then er dot has been expressed, and it is this expression times E phi. So now we are ready to do the simplification. I'm going to keep this page aside. Alright, so now let us consider the terms that have E phi in it. So note that this omega 2 R2 minus omega 1 R1 divided by 2 appears over here as well, and omega 2 R2 plus omega 1 R1 divided by R1 plus R2 appears over here. And so when you simplify the E phi terms, that is, if you collect all the terms in with E phi, then what will happen is this whole term, see, this is negative, and here when you take this multiplication, the two negatives make a positive, so this whole term gets cancelled, and what we are left with in the E phi direction is minus omega 2 R2 minus omega 1 R1 whole squared divided by 2 R2 minus R1 times sine theta E phi. That's the term that we are left with in the E phi direction. Next, let us consider the ER direction. Now in the ER direction, let's see here, we have two terms that are emerging from here and two terms that are emerging from here. Now you will notice that if you consider this, the product of this term containing the cos theta with this term, okay, and if you consider the corresponding term here, which is this guy multiplying with this guy, then you will see that all the terms are the same, and you have here a positive and here you have a negative, which means that those two terms are also going to cancel out. So essentially what we are going to have is this term will cancel, and here this guy will cancel. Okay, so basically what we will be left with is the following: negative of omega 1 R1 plus omega 2 R2 whole squared divided by 2 R1 plus R2 and then we will have plus omega 2 R2 minus omega 1 R1 whole squared divided by 2 R2 minus R1 cosine theta, and this whole thing is going to be in the direction of ER. So I'm just going to check if this is good. Indeed. So we can then say that the acceleration of the point C is given by this expression. So here then, so this is basically the final expression, and this is what I wanted to show in this video. Through this video I just wanted to show how you can use the direct differentiation approach to find out velocity, accelerations, and so on. The thing to keep in mind in this video is that, or in this approach, is that when we took the direct derivative, we had to differentiate the unit vectors as well, because the velocity was expressed in terms of rotating unit vectors. Often the use of rotating unit vectors is very advantageous because it is easier to intuitively understand the motion of a certain particle or a rigid body when you express in terms of rotating frames. So with that, what we'll do is we'll go to the next part of the video where we'll briefly just analyze the results that we have so far and try to put these results or try to understand physically or intuitively. We'll try to understand how this planetary gear motion is going to take place, and what kind of motions are we expecting to see for the planetary gear under different conditions. So there are some interesting observations that we can make. So I'm going to look into or discuss that next, so that we have an intuitive understanding of how the motion, what is the motion of the planetary gear. So there are three special cases that I would just like to point out. One is under what situation will the planetary gear go around the sun but not rotate, yeah. So this is an interesting case, because what we are saying is that you can have a scenario where this planet, as it goes around the sun, it takes a curvilinear path. It does not have any rotation, which means that as it goes around the sun, it's not that it is spinning. Its orientation is going to be exactly the same as it goes from one point to another. Okay, so it's somewhat like this, that if this is the ring gear and this is the sun gear, here is the planet. Okay, so if I assume that this point on the planet is P and this point on the planet is Q, and P and Q, let's say, are diametrically opposite, and they are at a certain instant, they are pointing at, let's say, some angle alpha from the horizontal. Then when the planet is here, right, at that time also the point P and the point Q are pointing in the same direction. So this is still P is here, Q is here, okay, and they are pointing in the same direction. So essentially the planet is not rotating. It is, the center of the planet is following a curvilinear path. That is true, but the planet as a rigid body is not rotating. Okay, so this kind of motion of a rigid body is not a rotational motion, it's a curvilinear motion, because rotation is only when the orientation of the rigid body is changing. Here, as you can see, from this position to this position, the orientation of the rigid body has not changed. P to Q is still making an angle of alpha from the horizontal. Okay, so with respect to a fixed reference frame, the orientation of P with respect to Q or Q with respect to P has not changed, which means that the rigid body is not rotating. Okay, so So that is one. So P, however, is indeed going in some. Let me try to see here. The center of the gear is going in a circle. Yeah, but that is a curvilinear motion. The orientation of the object is not changing. Okay, so the question is, under what situation will this happen? Under what situation will the planetary gear not be rotating? Okay, so this will happen if you consider the planetary gear by itself, and let's say this is the point P and this is the point Q, and this is the point A, center of the sun gear, and this is the point B, center of the planet. Now at a given instant, we know that the velocity of the point Q is omega 2 r2, and it is perpendicular to AB, and the velocity of the point P is omega 1 r1. Okay, now the situation under which the planet will not rotate is the situation where both P and Q have the same velocities. Okay, now in a rigid body, if 2 points on the rigid body have the same velocity, that means when we say same velocity, it means the same magnitude and the same direction. Okay, it's not just the magnitude, it is both magnitude and direction. When 2 points on a rigid body, 2 points fixed to a particular rigid body, has the same velocity, meaning the same magnitude and the same direction, okay, that would mean that that particular rigid body is not rotating. Because in a rotating rigid body, no 2 points fixed to that rigid body can have the same velocity, meaning the same magnitude and the same direction. That cannot happen. If that happens, then the rigid body is not rotating. Okay, in a rotating rigid body, you cannot have 2 points P and Q with the same velocity. Okay, any 2 points on a rigid body will rotate, one will rotate with respect to the other at the angular velocity of the rigid body. So in other words, if I take a rigid body and if I take any 2 points on a rigid body, any 2 points fixed to the rigid body, one is rotating with respect to the other at the angular velocity of the rigid body. Okay, that is just in general true for any 2 points on a rigid body. Now, so what is the condition therefore that the rigid body is not rotating? That I take any 2 points on the rigid body and I impose the condition that they have the same velocity, meaning same magnitude, same direction. If that happens, then that rigid body is not rotating. So in this case, we know that P and Q do have the same direction, okay, but it will have a same velocity if omega 1 r1 is equal to omega 2 r2. Okay, then P and Q have same velocity, magnitude and direction. Therefore, planet not rotating. So that is the condition under which the planet or the planetary gear will have no rotation. Now let us take another situation, or let us study another condition, and that is under what condition. So this is number 2. Under what condition will the planet remain at the same location. So what this means is that, so let's say this is my ring gear, this is the sun gear, and this is the planet. I want to find a situation where the planet can be spinning. So keep in mind that this is going with omega 1 and this is going with omega 2. The planet can be spinning, and this is point A and this is point B, but the point B does not move at all. Under what condition will it so happen that the planet can be spinning on its axis and it is not going around the sun? Under what condition can that happen? Well, that can happen if the instantaneous center, the center of rotation of this gear, lies exactly at the point B. What that'll cause is that, so imagine that here is the planet, this is point B, this is point A, okay, and what happens if the velocity of the point B becomes equal to 0? Now we have calculated the velocity of the point B, but I don't think I need to invoke, I don't need to invoke that, because I don't need to go back to the basic kinematics to make that observation. We can make the observation through an intuitive understanding of the angular speeds. So the idea is that, and now this is the point P and this is the point Q. Now what happens if so here the velocity is omega 2 r2. Okay, now what happens if actually the sun gear omega 1 is actually going in the reverse direction? So omega 2 is going clockwise, let's say omega 1 is going counterclockwise, which means that this point over here, which is basically the point P, and this is our point Q. So Q is going in this direction, but P is going in the reverse direction. So let's say that P is going like this. So here the velocity is omega 1 r1. Now what happens if omega 1 r1 is equal to omega 2 r2? Then the instantaneous center of rotation is going to be this point B, and it's not only going to be an instantaneous center, it's going to B will remain the center of rotation, because omega 2 r2 and omega 1 r1 are constant velocities. So the center is always going to be over here. So this will be a scenario where what will happen is that, and actually for the sake of just thinking what is the right way to express this, because I would say that I would call this minus omega 1 r1, because we have our convention is that omega 1 is in the clockwise direction as well. So that's why I would represent the this as negative omega 1 r1. But essentially imagine that a scenario where the point Q is going in this direction, point P is going in this direction, so that the center of rotation of the planet happens to be at the center of the planet itself. And in that case what will happen is that the planet will just keep spinning, and it will just keep spinning with an angular speed of how much is it going to be? It's going to be it's going to be omega 2 r2 divided by r3. So that's going to be the angular velocity with which the planetary gear is going to spin, but the condition under which that will happen is when, as you can see, omega 2 r2 is equal to minus omega 1 r1, or when omega 2 r2 plus omega 1 r1 is equal to 0. When that happens, so clearly this is saying that omega 2 and r2 need to be in the opposite direction, but when this happens, then the then planet keeps spinning with center at the same location. So this is another interesting case that can happen. So imagine that the understanding of these kind of special cases can help us do design of planetary gears, especially since planetary gears are used in transmissions to cause various amounts of gear ratios and to cause the speeds to be different from a driven gear and a driver gear and a driven gear. So this is the case too. Another case that is interesting is when the motion of the gear happens in a phase-locked manner. So third is, under what condition will the motion of the planetary gear be phase locked? That means the planetary gear will always be facing the same side of the planetary gear will be facing the sun, much like the moon is phase locked with the earth. We always see the same side of the moon. So under what condition will that happen? So this is a case where, so let's say this is our ring gear, this is the sun, here is the planet. So this is A and that's B. Let me just join them. So you can see that, let's say this part, this half of the planet is facing the sun. Now when the planet is here, and so let's call this point C and let's call this point D. When the planet is here, okay, and B has moved to a point like this, then it's still C and D, that's facing the planet. Under what condition will this happen? So this is the phase locked condition. So this will happen if the angular velocity theta dot becomes equal to 0. So phase locking when theta dot is equal to 0. Remember, theta is used to give the position of a point with respect to the line AB. Okay. Now, if this theta does not change anymore, right, that means that whichever half was, or whichever semicircle was facing the sun gear will always be facing the sun gear as the rotation happens. So this can also be imposed. Theta dot is equal to 0 is rather easy to impose. So if you take the expression of theta dot, which is essentially, let me just see, I did have the expression. Let me just see here. Oh, there we go. So here is the expression for theta dot. So if we put theta dot equals 0, then we get that phase locked condition. So let me just take a look. It's omega 2 R2 minus omega 1 R1 divided by R2 minus R1 minus this guy. Okay, so let's impose this condition here. So omega 2 R2 minus omega 1 R1 divided by R2 minus R1 minus omega 1 R1 plus omega 2 R2 divided by R1 plus R2. So this has to be equal to 0 to create that phase locking. So essentially what you need is omega 2 R2 minus omega 1 R1 times R1 plus R2 is equal to omega 1 R1 plus omega 2 R2 times R2 minus R1, and this is going to give us omega 2 R2 R1 minus omega 1 R1 squared plus omega 2 R2 squared minus omega 1 R1 R2 is equal to omega 1 R1 R2 plus omega 2 R2 squared minus omega 1 R1 squared minus omega 2 R1 R2. So let's see if we have some cancellations. We have these cancellations here, right? So what we are left with is 2 times omega 2 R1 R2 is equal to 2 times omega 1 R1 R2, which implies omega 2 is equal to omega 1. So whenever the angular velocity omega 2 becomes equal to omega 1, that is when the ring gear and the sun gear have the same angular velocities, then what will happen is that the planetary gear is going to be phase locked, and it's almost going to be like the planetary gear becomes a part of the sun gear, because it is rigidly, almost like rigidly connected, because this half is always going to face the sun gear. So which means that it's almost like they are virtually rigidly attached, okay? Because that's what happens when they are rigidly attached. One part cannot move with respect to other, and that is what is happening with the phase locking. And it makes sense that omega 2 equals omega 1 will lead to that, because essentially when you have the outer part and the inner part, that is the point P and point Q. So if this is point P and this is point Q, if P and Q are rotating with the same angular velocity about the point A, then the overall object is rotating with A as the instantaneous center, which is also the instantaneous center of the sun. So it's almost like the planet and the sun have become one locked unit. You see, the sun is rotating at omega 1, and P and Q are rotating with its center at A, which means that P and Q are rotating with the same center as the sun, which means that the planet and the sun are rotating as one rigid body, right? And that's the case when it is phase locked. So that's the phase locking scenario. So these were some special cases that happen in a planetary gear under different angular speed conditions. So I wanted to illustrate these different cases, and that is going to be it for this video. Thank you so much.